I was asked to give a talk looking at the big picture internet. And so I'm actually going to try and look at the big picture internet, trying to take a step back and kind of look at where do we come from, what's driving where we are today, and what's likely to play out in the future. So this only briefly kind of touches upon NDN per se, but tries to put a lot of this work into a far, far broader context of the big picture internet, one way or another. So where do we start with all this? I would actually say that the early antecedents were, 125 years ago, when we actually managed to get controllable electric power, thank you to Andressando Volta, and another 20 odd years, Hans Christian Ørsted demonstrated the connection between electric current and magnetism. And then another 10 years in research to look at a system of sending texts, simple text, pointers, using electric current. And its commercial use was actually in railway signalling in the UK. 1840s, another 10 years. And a keypad was used by Samuel Morse to do the telegraph system. And it was about then that things moved from early experiments and initial sort of limited deployment into more mainstream. And by 1861, the telegraph boom was well and truly in place, particularly in the United States. And a mere 10 years later, there were undersea cables going across the Atlantic to sort of connect up Europe and America, which was where the major commercial impost was. There was a telegraph boom. It was, I think, every bit as big as the internet boom, if not bigger. Initially, investment activity actually came predominantly from the United Kingdom. By 1882, sorry, I can't type, British companies owned and operated 2/3 of the world's telegraph systems. At the time, the British Empire, which was the largest commercial and trading empire of the world at that time, the telegraph was indispensable, which was why they invested heavily in laying undersea telegraph systems. There was also a major boom in the United States. And if you combine that communications with transportation in the railway, all of a sudden, in the late 19th century, there was this massive opportunity of projection of power and aggregation, the Gilded Age and the rise of the modern, at the time, large but not quite multinational, but it quickly turned multinational, industrial conglomerate. Private monopolies were all powerful inside this area. So the internet kind of came from its antecedents in telegraphy, but what really made the change, of course, was the telephone. 1876 at the World Expo, and they first exhibited something you could talk into, and it took off immediately. The major telegraph operator at the time, Western Union, thought this was merely a fad. Reminds me a bit of AI today, merely a fad. And Western Union never really fully appreciated that this was going to kill it until it killed it. It was just too late. The initial work in telephony was haphazard, privately organised, in a massively deregulated market space, and it was extremely chaotic. The organisation of this environment actually took another 30 years in various countries, and lots and lots and lots of small, ineffectual communication systems that did not interconnect was serving nobody. But interestingly, the American Telephone and Telegraph Company was one of the first to see an encompassing national vision. And Theodore Vail, the president of AT&T at the time, actually did a deal with the US Congress, known as the Kingsbury Commitment in 1913. And it said, look, we've got this dog of a company called Western Union Telegraph. We will get rid of it. We will divest it. In return, we want a monopoly on all telephony in the United States of America. One policy, one system, one service. which was kind of breathtaking that Congress bought it at the time. The idea that a private company would work in the public interest. Breathtaking and unrealistic, because it only lasted about 10 years before it all fell apart and the monopoly was so entrenched it couldn't be dismantled. Other countries looked at this and went, oh, not really sure about doing it in private hands. Why don't we make it a national monopoly? And so in many, many other countries, the telegraph, which was also a monopoly in many countries, simply subsumed all these small telephone operators and became national telcos. And that lasted for most of the 20th century. Now, if you think about the telephone network, and some of you might still remember it, you might even remember what a handset was at some point. The telephone network connected dumb handsets to handsets. It kind of took the microphone and speaker at one and connected it to the speaker and microphone at the other end. You couldn't contact the network. The network was completely transparent. The network was a set of real-time virtual circuits that were created on demand and torn down by demand, and the edge devices were incredibly simple. And so you can think of the telephone network as a network-centric architecture with incredibly minimal functionality in the edge devices. Basically, what it was intended to do was to strap up virtual circuits on demand, maintain them, and by virtual circuit, I mean one of the hardest ones, synchronous, switching time. Maintain these circuits for the length of a call, and then tear it all down once the call was over. That was an astonishing achievement. And even today, I marvel at the ability to switch time. Because of all the things, that's one of the hardest to actually get right. Now, the original concept for computer networking was based entirely on telephony. The network was actually there to enable computers to exchange data with each other. And it wasn't a broadcast model or a multicast model or any other form of multi-party communications model. In the wide area network, it was completely borrowed from the telephone system. So computers made point-to-point connections. They established virtual circuits, and effectively they were able to initiate or receive calls. You couldn't call the network was just invisible. And quite frankly, it didn't really matter what the network was built of. They just effectively created connections, exchanged data, and then tore the connection down. And this model still persists today, if there are any X25 networks out there, in the X25 network style, which is basically the voice network using digital endpoints rather than human endpoints, and not much changed. What was the change? I think the change was the datagram. As soon as you accommodated these small quantums of data that existed on their own, you revolutionized what computer networks can do that voice networks, telephone networks couldn't. You segment the data into independent packets. The network switching function is stateless. All the endpoints are uniquely addressed. Every packet tells the network where it's going to, and it's the network's job to either deliver the packet or drop it. And that's it. Single network-wide addressing model, single routing model, a very simple datagram delivery mechanism, and hop-by-hop destination-based packet forwarding. I say circa 1980s, and that's probably true when it was implemented with some level of scale. The original elements of this design come straight from the 1960s. And quite frankly, it hasn't really changed all that much from that basic model. In the same way that the telephone network used telephone numbers, these are computer networks, these datagram packet networks, used the analogous form of endpoint addressing, which was basically numbers for computers. And those numbers were carried inside the data. The only difference here is rather than making virtual circuits so that the interior data does not need to sort of have its own addresses and suffer its own fate in switching, inside a datagram network, there are no circuits. There's no help. Every packet is its own independent adventure. You're stripping out almost the major thing that distinguished the telephone network: the creation and destruction of virtual circuits that locked in time. They were time synchronized virtual circuits. The internet didn't need it because, in effect, there was no timing. Each data element was its own fate, either made it or didn't on its own. And so from that, you get a very classic internet architecture of the 1980s, where a lot of the intelligence was not in the network. Most of the intelligence was actually at the edge. The network did not do virtual circuits, did not guarantee packet delivery in order, did not even guarantee packet delivery. This was about the worst possible network you could possibly build. The intelligence was actually at either end in the computers that were running the transmission control protocol, or at the time called TCP/IP, which actually made sense of all these packets being out of order, all these packets, perhaps some of them being dropped, creating reliable stream flows on top of an unreliable substrate. And that was the true value of the internet. Why did it take off? Because the thing that was killing telephone networks, really the major cost element, was actually in these circuit switches. Virtual circuits and time synchronization was astonishingly expensive. And if you got rid of that from the network, you actually found yourself with a network that was almost 1,000 times cheaper per unit of data carried. Minimal design, maximal flexibility, efficiency, everything's been pushed out to the edge. And so all those things that you worry about when you're trying to do, like voice, as we're doing now, or video, which is flow control, jitter, stability, mitigation of packet loss, reliability, the network just does not care. It has no idea of actually what it's doing. All of that functionality is pushed out to the edge, to the computers at either end. Now, the network service provider is not paying for those computers. You and I are. That cost has been externalized from the network. And so by comparison with running a telephone network, running an IP network is cheap and simple. Doesn't need to work very well because of the end systems that fix everything up. Now, the initial work in this was not exactly massive. The initial APNIC was just a number of sites with US military contracts. The NSFnet, the National Science Foundation network of the late 1980s, was a number of universities, firstly in the US and then a number of other academic and research places around the world. But by the mid-90s, people started bringing computers home. The home PC was sort of a thing. And all of a sudden, connectivity via a network was amazingly popular. And out of that came just runaway growth. All of a sudden, this network was doubling in size around about every year. That is really hard to cope with. And like you look at road systems in modern cities, if the number of cars on the road doubled every year, we can't build roads fast enough. We just can't. And you get structural traffic congestion of unbelievable proportion. I think the traffic in LA is bad. Look at Bangkok. Look at Kuala Lumpur. Once you get scaling pressure on systems that take time, capital, and resources to organize and build, you get runaway congestion and failure. And that was the fate that was so close for the internet, that our underlying connectivity, our routing systems, everything was under incredible stress from scaling. And the result was to look again and again at what we were doing with addressing routing and connectivity, those elements of infrastructure that were just finding it difficult to build. Our response was to actually, again, take another step away from the telephone operators. Because in the world of telephony, every telephone operator is a peer of every other. Australia's got one, Canada's got one, America's got one. They've all got one, and no one's a provider to anyone else. No one's a customer. We are peers at a national level. Everyone was equal. And so in the internet, to cope with growth, we started to role differentiate. And oddly enough, that created a set of flows of money which was unusual. There were, in the 1990s, around about a handful, and by a handful, it's contentious, but I'd say around 5 folk who ran large-scale, almost global networks for everyone else. They moved packets around the world. We called them Tier 1 transits. Unet was one, Level 3 was one, and so on. Below that were a number of kind of mid-level networks which served a geographic area normally. So it might have been Northwest America. It might have been the area around LA called SurfNet, I think, at the time, and so on. They bought their global transit service from someone else, but provided service across a defined geography. And at one level down, there are a whole bunch of retail access networks. And the way it worked is that role specialization allowed an access network to actually have a viable business selling connectivity to the global internet without ever having to build it beyond their access region. That was other people's problem. And yes, you paid those other people money to get your packets delivered and collect packets from them, but you didn't have to build it yourself. And that kind of divide and conquer was relatively new for everyone in this industry. Normally, every service provider was, as much as possible, a full service provider for everything. Success, though, is a whole bunch of problems all at once, and particularly in scaling. In the 80s, when TCP was being designed for the second time, actually, we came up with a 32-bit protocol address structure. 4 billion possible connected computers, but we divided it up into classes. So there were things called Class A's that actually managed to connect up to 17 billion computers, and there were about 128 Class A addresses. There were Class B's with 16-bit fields and Class C's with 24 bits. We were running out of B's. And even then in 1990, it was pretty obvious that we had about 3 years to go, and then the internet was going to run out of addresses in the Class B space and die a horrible death. Now, the thing about edge-based networks is that they're really difficult to change. In the telephone system, we've renumbered the telephone network numerous times, and no one's noticed because the guts of functionality is inside the network. In the IP world, you have to change every connected device. And that is a scaling problem all of its own. And the incentives to change are not by command, they're by market incentives. The internet runs on a market. And so we start to look at this going, if we're running out of uniquely addressing every computer, why do we need to connect and uniquely address every single computer? And oddly enough, the industry, without any conscious decision, has gone, too hard. Let's not do that. Let's dispense with unique addresses for clients and simply give them to servers. And so instead of a peer-to-peer network where anyone can be a client and anyone can be a server, we move to an asymmetric network where clients are you and I running stuff at homes, in offices, wherever. And what we do is access services provided exclusively by service provider platforms, not by other clients. And so to get out of that scaling pressure with the use of addresses, and that scaling pressure with the cost of uniqueness, we turned into asymmetric client-server networks. In essence, what happened is that only services need persistence of identity. No one cares about clients. No one cares about their identity until they connect to a server, in which case it's good enough to borrow an address, use it for the length of the service transaction, and then throw it back into the address pool for someone else to use. So clients are behind network address translators these days. They're behind NATs, and that's global. We've managed to cram close to 30 billion odd devices into today's network and do so in an address space which is less than 3 billion in terms of its useful space. And this 10-to-1 cramming has been because we're sharing addresses via network address translation. They're the mainstay of today's network. Servers need a service identity. That's not the same as a persistent address. That's simply a service identity. And that model of service provision has changed a lot over time. So how has that changed? Well, let's look at the old model. And this is one, say, for Microsoft, which placed its new versions of Windows in a whole forest of computers in a data center in Seattle. The world had to go there to collect the updates. That was horrendously inefficient and created a massive set of black holes wherever popular content was being driven. And the result was a lot of folk were at the raw end of the stick. I remember this one, and it's actually only from 2011, which is not that long ago, where Facebook is saying, well, we set up our global data centers, 2 on the West Coast, 1 on the East Coast, and we've noticed that the rest of the world is kind of having a hard time getting to us. And the answer is, yeah, right. Physics gets in the way, and some things are just a long, long way away. And so we tricked or fell into, and it wasn't quite deliberate, but content distribution networks, of distributing the content around to the edges of the network so that clients don't need to transit the network. They just need to get to the closest data center at their closest edge. This has taken over the internet very, very quickly, as fast as the rise of AI in recent years. And all of a sudden, we're replicating content as close as we can to large user populations. And kind of everyone wins, because if distance is cost, reducing that distance and pre-provisioning local centers basically creates lower cost, much higher speeds, and oddly enough, happy customers. How do you do this? Well, there was a lot of interest in Anycast, where, and Cloudflare have used this a lot, where you use the same address in multiple locations. So the DNS maps the service name to an IP address, and then you rely on routing to get you to the closest address point. Yes, but no, because the network is not long and stringy, it's actually short, fat, and dense. And what that means, when you look at the average AS path length, is at most around 5 or 6. The network is not very good at discriminating between geographically near and geographically far. They can make extremely poor selection models. And so Anycast works well for short, simple transactions, which can tolerate some degree of mismatch. But if you're going to do video streaming or something in large scale and use Anycast, IP Anycast for this, the service quality is shocking, because the amount of sort of bad decisions made in routing is enough to throw the performance of the entire platform skewed. So how do other folk do it? And this is a classic answer from Akamai. You use the DNS, the naming system, to perform the steering of users to servers. So this is an example. I'm located in Sydney. I'm looking for a broadcaster, which is Australian-based, and it directs me to an IP address, which is located in Sydney. I do exactly the same query from a system in Germany, and it will direct me, that DNS name, the same name, will now resolve to a server located in Frankfurt in Germany. Why? Because the DNS, unlike routing, can actually make extremely fine-grained decisions as to performance and what is closest in terms of optimizing performance of the service. So we're using the name now to steer content. The IP address is merely a convenience to stop things getting confused with each other, but it's not used as an alias for location or performance selection. Now, the assumption, of course, is that no one's using Google, Cloudflare, or Quad9 resolvers, because the assumption is that you and your DNS recursive resolver are basically at the same location. And if you're using a remote resolver, everything looks pretty stuffed. On the other hand, the level of use of those open resolvers is kind of sufficiently small that it's a livable answer. And we can, in doing this kind of DNS steering, adapt which server you go to based not only on what's fastest, but based on what's under the least load. What can offer you the best service for the transaction you want when there's a variety of servers you can select. But you can go one further. You can actually do this steering inside the application. And YouTube is a classic in doing this, where it breaks the content into separate service chunks each of which have their own handle. Let's call it a URL for convenience sake. And so you have a number of platforms, each with their own IP address, it's location based. And in essence, while the application plays out the YouTube video, it is constantly looking at nearby servers that can service the same chunk and experimenting with what offers the best throughput and the optimal performance for you as a client. And so now it's the application itself that is performing the steering of content to client. And so the APNIC used a lot for the DNS, not really good for much else. DNS steering, well, if you don't quite understand what you're doing, like live stream video or voice, where you can't chunk it up in advance, is fine for those kinds of service transactions. And once you've got video streaming or similar decomposable data, application steering gives the best answers. So what's the internet as a result of all this? Users don't connect to servers. That doesn't happen anymore. What we actually do is get mapped to the closest service delivery point that eliminates much of the internet, reduces the network to distances which are as close to the user as we possibly can. The network's moving in to the edge. And what we see of the internet now is just a hop across the last mile access network. So what does this mean? Well, oddly enough, it's access networks are getting faster. That gives us high volume streaming. That gives us high capacity networking, which gives us economies of scale. And all of this just simply means bigger induces faster and cheaper in the networks we build. How? Well, the one observation is this is not a command and control economy. Unlike the telephone networks of old, there is no open roadmap on where we are going. It is just a bunch of providers desperately vying with each other to have the best and most cost-effective offerings on the marketplace. Fastly and Akamai are competitors quite deliberately, and they're both trying to do a better deal for the folk who have content hosted on their networks. And so it's competitive pressures that are driving it. You go, well, that's good, isn't it? But you bring in another observation and go, well, it's actually not that highly competitive. Oddly enough, if you scratch the internet apart, you'll find 5 massive megaliths and not much at all else. So if it's not competition, what's driving this? I would actually argue that the major driver of change is actually Moore's law. The amount of density of gates we can put on silicon chips. And now that we're down to 3 nanometer tracks on silicon, which is the latest version being used, I think, by Apple with their trillion gate chip, then what actually goes on is the cost per gate, the cost of processing keeps on coming down, and it's opportunity cost that is driving all of this work in the market. The economics of chip evolution have basically meant that each technology has about a 5-year horizon before it becomes too expensive, too slow, and doesn't work. There's no 10-year business plan. And if you have one, you're dreaming. Because quite frankly, as long as Moore's law is ascended in our world, nothing has more than 5 years of viability in the marketplace. Moore's law is indeed horrendously brutal. And that's actually led to the emergence of these amazingly large digital monoliths in our space. What would be much more surprising if it was still highly competitive and no one had managed to dominate. Because once you get something that's moving that quickly, they tend to consolidate to reduce risk. Smaller entities always fail. Even the larger entities get sucked up by the largest, and only the very largest can afford to buy their future. So yes, once you get rich enough, it's not the current competition that worries you, it's future competition. And that's behind a huge amount of the moves by these very largest folk. So all of a sudden, we're being driven by abundance and scale. And networks have shrunk. We don't share the transit systems. Each of these large entities is so large, they build their own global distribution networks and use it exclusively. They have command of that much capital and resource. And it's the content distributors who take that abundance and pre-provision content to the edge. we no longer rely on networks to do just-in-time delivery. The entire network is now working on basically pre-provisioning. What does that mean? We've moved beyond address-based network architectures. Addresses are merely a relative concept about stopping traffic getting confused in a datagram network. They're used in the packets to stop the routers getting confused. But by and large, routing is DNS service selection, and persistent service names are what we use on the internet. Even the fundamentals of security are based on the name of the thing you want to go to in TLS and have nothing to do with its address. The DNS is the mapping of the service description to a profile that lets you connect to a service. Is this named data networking? Is this the NDN we were talking about? And I would answer, well, yes and no. What we don't do is change basic packet forwarding. That's still IP addressing. Endpoint addressing is still there to some extent. It's just that if you're a client, it has no permanence. And even if you're a server, it's not the service that is being addressed. Services are being named. That's not quite the same as naming data. So in today's internet architecture, and I make a note that it's probably not an architecture. It's not structured, it's not designed. It's just an outcome of technical evolution. That blending that we have today of a named service environment with IP transport is I reckon, about as good as it's going to get for named data networking. It is not really going to change beyond that model. So all of this is due, oddly enough, to the underlying pressures of continued refinement of silicon chip technology. That phenomenal pressure of basically doubling the performance and halving the unit cost every 2 years has wrought about extraordinary change extremely quickly. We could not have contemplated AI 5 years ago, just not even in your wildest dreams. And quite frankly, the only reason why you're going to spend billions of dollars building an AI data center today is in the thought, or maybe it's faith, that in 2 years' time, it'll be half as expensive. So you've got to move quickly and move hard in order to claim dominance in a market that will become a commodity in the future. That's the thinking behind why we're building these exotic and currently extremely expensive facilities. The feeling is if you get there first, you can ride Moore's law to make it cheaper and more accessible. But that kind of places a degree of faith in Moore's law, which is irrational. Moore's law is going to stop. The laws of physics are going to assert themselves pretty quickly. And quite frankly, smaller than 2 nanometer tracks get into extraordinary problems with electron tunneling, stability of manufacturing processes, and so on. 3D silicon cages is probably the way out of this, but quite frankly, neither you nor I, nor anyone else on this planet know how to build them at the size and scale that this industry needs. So what happens when Moore's law kind of comes to this block of, well, physics can't make it any smaller and cheaper? We don't know. We simply don't know. So that propellant of the last 50 years is going to run out of steam at some point. And my suspicion is that some point is in the next 10, maybe even as little as 5 years. And beyond that, we have no idea where this is heading. Hopefully that's enough of a big picture to give you a feel, I suppose, of where I see the internet coming from and heading to. There is about, 2 minutes for questions, so I will come out of sharing, and if anyone's got any, I will frankly try and answer them. Thank you.
Okay, so we have a question from Huston.
Yes, I can see that question about how easy would it be to map the current DNS infrastructure into an NDN transport. And the answer is, in some ways, why would you? The DNS infrastructure is a case of resolution of names as distinct from getting to a service point. The whole job of the DNS is to make the next packet a packet that actually is the service packet directed to the service entity. Now, that resolution infrastructure of trying to map service names and service attributes into what protocol, what address, etc., what form of packet needs to happen, is almost an intrinsic property of having an underlying addressing-based platform working on below a naming-based service environment. The NDN idea was to actually just make everything names to start with. And in essence, you're pushing that resolution problem into a traffic steering problem into NDN routers. I suspect that the underlying abstract model of NDN routing is more like what we wanted it from the 1980s. And I'm really not sure how well it translates into what we want from switching and networking in 2025. The whole idea of steerable, load-sensitive application steering, which is what drives today's internet, where the application is making choices between different delivery platforms to optimize the user experience, doesn't strike me as one that readily translates into NDN. But I am not as familiar with NDN as I should be. Maybe there are answers there. But my suspicion is you're trying to solve subtly different problems when you say, well, why don't you just make the DNS work on NDN? I'm not sure that's sort of where answers might lie. But it's a great question. Thank you.
I'm trying to figure out what to say. I think, Geoff, in all these discussions, I see one important word that did not appear as it should have, which is security.
Oh, security is a mess. Not only was it an afterthought, it was a poor afterthought bolted onto an existing framework and bolted on in such a way that every single time we've tried, we've simply kind of declared it as a success, even though we're, as an entire community, spending a few $1 trillion on cyber defense. You could never say that security was the sole problem in any way in today's internet. We have banked on name-based authenticity as our cornerstone for security today, the TLS model. And we're finding that to be weak and inappropriate. The trust that we place in it is misplaced and easily subverted. Now, I wish I knew how to do that better. Also, I wish I knew how to do it incrementally so I don't have to reprogram all those 30 billion devices that form part of the internet. But those kinds of thoughts are well beyond my own personal meager capability. So it is a massive unsolved problem, Leisha. And you know, I'm not sure where lies a better truth, but I would say if we could separate out the infrastructure of the existing TLS PKI and get rid of it and push that back into the DNS, we might have a hope of making the naming system authenticatable, whereas today it is only weakly so. And perhaps that might help. Beyond that, I kind of run out of ideas pretty quickly, but I'm not no different from anyone else in this world. We haven't found silver bullets yet to try and sort of solve this problem in any meaningful way.
I think you and I agree there's no unsecured communication. And
yes, we haven't got there.
Right. So therefore, the only place you can set up a secure connection with are all in the clouds. And that's how we became controlled by the clouds. I think that you hinted on one thing, that is the asymmetry between the client and the servers. Servers have identities. Servers have keys that others can verify. Web PKI or not, you like it or not, but that's how we do verification today. And that's how I think is the one major factor we got into where we are. I think, due to the time difference, you missed this morning's discussion, where the one new direction is to give everyone a name for example, DNS name, and then everyone will get a certificate. Then everyone can directly communicate by named secured data as a future direction. You talked about there's no way to reprogram 30 trillion or 30 billion devices. I fully agree with you. The question is,
Yes.
Can we start from now, just add the new entities that can do this new way of communication in a secured fashion and not controlled by the cloud? As a new way to start the new life.
I think that there are some elements, Leisha, which are helpful. X509 certificates are merely a promise about the future. I go to a certificate authority and say, I am me, and it issues a certificate to say, everyone else, you should trust Geoff into the future because in the past, Geoff passed this test. That's not security, that's faith. If we want real security, then these kinds of tests of authenticity, the delivering of credentials, the association of credentials with the transaction you are doing need to be real time, not based on events that happened in some past with some other parties. We actually do have a functional network these days, which is probably not what X509 was built upon. And by stripping out some of that historical baggage and looking harder at what we can do with a live network and the way we map names into attributes of names, which is really what the DNS is all about. I think there are some promises there with an extended and expanded use of naming systems in security. But, as I said, I'm not the expert here. I'm only dimly aware of some directions that might be useful. And it's up to others, I think, to follow down those paths.
I just wanted to point out that what Geoff just said is the exact opposite. I agree with what he just said about you verify the identity, the authenticity at some point in time, and the only thing that you're proven is what was true at that point in time and nothing about that point onwards. So I was talking to Varun during the lunch break, and I sort of told him the same thing in different terms. If you're gonna tell this to somebody like a cryptographer that you have long-term keys that are valid forever or close to forever, then they're gonna start screaming. So yeah, I mean, I don't. It's not a question or anything. It's just a comment on this. So there's a fundamental problem here. Although, if I can turn this into a question, do you, Geoff, have any hints of what form this authenticity, this proof of authenticity could take, so that it's more real time or close to real time?
What prevents you to be real time? That's a part I don't understand.
What's the proof itself? If the proof is
what is not real time?
Well, that if you do it once and then you rely on it a year from now, that's not real time, right?
It's not so much you prove it once. You have an identifier, you prove it, you have the crypto to prove you are the owner of the identifier.
Yeah.
And this proof will continuously be refreshed.
Right. Yeah.
So it's always valid.
Exactly. It's the second part, the continuously being refreshed,
Right.
that we did not say earlier in the discussion.
Oh, okay.
Right?
So then we said so.
Yes.
We have learned from all these years of internet crypto designs, everything has to be soft state. The hard state does not work because failures always happen unexpectedly.
Yeah. And there needs to be also a way, as a consequence of this, then when there is a failure, then you need to then you have to associate your identity with a new set of keys.
I'd rather say that, like a soft state, you continuously refresh it instead of waiting until a failure happens to repair.
Oh, I see what you mean.
Right.
Sure.
That's how protocol
There may
generally
be
works.
performance or scaling implications with that. So you need to find a trade-off, I guess.
we haven't decided how to do it yet. How do you know there's a scaling issues?
Well, because other parties need to communicate with you, so they need to know what your identity is.
Right.
Right? Mm-hmm. So how do they find that out? How do they know that it's valid? So if it continues to change, then it means every time I talk to you, I have to redo the process. Assuming this process is not taking a zero amount of time, right? That's what it
I'll take a far remote analogy. Think about the global routing system, right? The status of the nodes of the links change over time, especially over large scale. How we manage to keep the real-time communication going instead of bump into a failed link and try to get around it at the time of need is that we preemptively and proactively maintain this connected state. So whenever the traffic comes, it gets delivered in real time. I think for the trust relations, this is a word we have been saying lately. We really need a trust plane. And the trust relations, security relations between all the parties, it's already exist in human society. The question is how we can reflect that into the cyberspace and maintain that connection or relation within the cyberspace. Continuously check, recheck, refresh the relations, the liveness of your certificate, everything within the time limit, things like that. So once this trust relations get maintained, then you just utilize that relation for the secure communications whenever you want to communicate. Instead of today's situation where you want to set up a connection and you at that moment I'll say, I need to verify the server. The relation between you and the server exists. Whether you talk to the server or not talk to the server. This is current practice of verifying the server at the time you set up a connection. It's just a little bizarre. But I understand why it works this way, because we really kind of patch the security on top of TCP connection without wanting to change a single bit of TCP. And therefore, when TCP connection doesn't exist,
exactly,
the so-called security relation no longer has a place to touch itself on.
That's when you create a tunnel.
So therefore, the TLS exists only when TCP is up.
Right.
And the TLS relation is gone when the TCP terminates.
Yeah.
But that's the artifact of how we bolted the so-called security on top of the existing protocol. That's not the nature of security or security relation themselves.
Or trust relations.
Or the trust relations, well, they use that word. Trust relations don't mean they trust each other, but rather there's a defined policies, how much you trust or otherwise you do not trust other parties. I think we talk about today, the data plane, the routing plane. You need a routing plane so that data knows where to go. And just as important, if not more important, is this trust plane. So that if we have to have secure communications, and we understand the relations with the party we're communicating, and maybe more often is that we know the crypto credential of the remote parties we're communicating with. This is really what I think Varun mentioned earlier this year during the panel discussion. Earlier today, about if everyone has identity, has a security credential, then building secure applications, decentralized or not, will become way easier. And that's the same thing reflected here. We're just talking about, instead of just building individual applications, it's generally speaking, when we want to have communications.
Right.
Yeah.
We fully agree for once.
Okay,
I'm
I
kidding.
think. Great.
We mostly agree on everything. At the end of the day, sometimes there's a miscommunication, but okay, no more questions. Okay, then I would like to thank Geoff again for joining us. Awesome presentation, as usual.
Thank you.
Yeah, thank you again, Geoff, for the great talk. Although I disagree with half of that.
That's okay. We make progress from disagreements rather than agreement. Thank you.
Right, thank you.